so we are labeling this. We are applying natural log. And now we are applying the limit to both sides. Limit as x approaches 0 from the right of natural log y equals limit as x approaches 0 from the right of the square root of x times natural log x. Again, at this point, I have to check again. This approaches 0. And natural log 0, let me refresh your memory on the graph. I know you know it. So as x approaches 0 from the right, this approaches negative infinity. So we are back to 0 times infinity, and I'm hoping that the symbol algebraic manipulation will help us here. I don't like bringing that square root of x, but I definitely don't want to bring this natural log. Limit as x approaches 0 from the right, natural log over 1 over the square root of x. I don't want this, but I have no choice, because I definitely don't want to bring this down. It will have a negative exponent with natural log, and then where do I go from there? Okay, so now the numerator is approaching infinity, negative infinity. That's not important. 1 over 0 from the right, this approaches 0, 1 over 0 approaches infinity. The sign is not important. So then now limit as x approaches 0 from the right, I will definitely change this piece into x to negative 1/2. And I hope for the best. When I differentiate the numerator, I have 1 over x. When I differentiate this, it's messy. Negative 1/2 x to negative 1/2 minus 1. Luckily, this 1 over x will come to the denominator as well, and the negative 2 will go to the top. So negative 2 in the numerator, and then I have x to negative 3/2 multiplied by x. X to negative 3/2 times x. Copy the base at the exponents. Negative 3/2 plus 1 is negative 1/2. Quite nice. It cleans up quite nicely. And then, of course, I'm going to bring it to the top. So limit as x approaches 0 from the right, from negative 2 the square root of x. It could have become very complicated, but it's quite nice. So I copy the beginning. Limit as x approaches 0 from the right, from natural log y equals 0. At this point, I'm ready to swap the operators. I have natural log. I'm going to put the function in. The function was x raised to the square root of x as x approaches 0 from the right. What could this be? And there is only one answer. One. Exactly. Because only natural log 1 is 0. Very good. So this was 0 raised to 0. Here's one limit that I honestly can't So 53, I think it's infinity if I see it correctly. Yes, I do see it correctly. So honestly, I have no idea what to do here. And you can say, how come? And I'll say, here's why. Obviously, when x approaches infinity, this is infinity. And when x approaches infinity, this is infinity. So this is our case, this. So we encountered everything except this one, not yet. And this is infinity minus infinity. There's nothing I can do here. I cannot apply natural log. I cannot do anything. I can only graph. I can't think of anything else. I need to see which of these functions grows faster. If this one grows faster, then this is small. The answer is infinity. If this one grows faster and this is small, then the answer is negative infinity, and I'm done. So when I graph y equals x, I graph this one. When I graph this one, I graph this. So which one goes to infinity faster? We can also do this, x and natural log x. And I'm just going to graph between 0 and something. So 0 to 400 with a scale of 50. Y minimum, I don't really care. I'm going to say -10. And y maximum, I don't know, let's say 400 with a scale of 50. They are not even close. This is y equals x, and the natural log is so low that it doesn't even get anywhere near at infinity. So then I have to draw a conclusion. So what is this limit? Yes, there is another way. I can go back to y equals and punch it in. It's another way. Or I can use the table. It doesn't matter. Whatever you want to do. Minus natural log x. And go to second and table. And just punch in 400. So I get a positive number. Let's say 800. I get a positive number. Let's say 10,000 to 100,000. I get a positive number, and it's always positive, and it's bigger and bigger and bigger. So obviously this is so much smaller than this, and there's nothing I can do. It's very clear. I can't use anything. I can't use L'Hopital's rule. I can only use either the graph or the table, or just think and realize that although this is an indeterminate case, it turns out to be infinity, which is very possible. So we looked at that one too. And we, yes?
I keep on looking back at the previous problem, and I'm a bit confused on how you came to the conclusion of 1.
You mean from here?
Yes.
Because only natural log 1 is 0.
Oh. No, I know.
That's okay. Or e raised to 0 is this. But okay. E raised to 0 is 1.
Okay.
Better?
Yes.
Thank you. Sorry about that. I should have. So let me refresh our memory on log base a of x is y. a, so this is equivalent to a raised to y equals x. So here we have natural log, which is base e, of something equals 0. So e raised to 0 equals 1. E raised to 0 equals 1. That's how we got the 1.
Thank you very much.
Thank you. So remember, this is the conversion between log equation and exponential equation.
Yeah.
Very good. So the only one that I did not find an example quickly for is this one. So if you want to give me another second, I may be able to find one of infinity raised to 0. Infinity raised to 0. Here it is, number 61. I wanted us to have all of them. Okay, so 61. In 61 we have natural log, limit as x approaches infinity from x raised to 1 over x. So obviously this approaches infinity, and this approaches 0. So now we can say that we even have the case infinity raised to 0. So we had examples of all powers, product, the difference which doesn't work, and L'Hopital's rule, 0 over 0, infinity over infinity. So like before, we will denote this by y, so it's x raised to 1 over x. As before, I apply natural log. And then the limit of the natural log when x approaches infinity is the same with the limit as x approaches infinity from natural log x over x. This is really so nice that I don't even have to do anything. As x approaches infinity, natural log approaches infinity. As x approaches 0, infinity. Done. L'Hopital's rule. Limit as x approaches infinity. The top prime, the denominator. So this is limit of 1 over x as x approaches infinity, and we know that this is 0. I copy the beginning and I copy the end. Limit as x approaches infinity from natural log y is 0. We already know the answer. I swap the operators. I have natural log y. Limit as x approaches infinity from natural log of that. So obviously this can only be 1 because natural log 1 is 0. So finally limit x approaches infinity from x raised to 1 over x is 1. And no, you cannot conclude and say, oh, but everything raised to 0 is 1. No. You cannot conclude that. It could have been anything else. Okay, so this section is finished. We do have 15 minutes left, and I would like to go through another exercise with a function that has slant asymptotes this time. Unless you have other ideas. We don't learn anything new in 4.5. We already studied everything about a function. We know everything about a function now. So would you like to use an example and from 4.5, or you have other ideas for me? Well, since you didn't say anything, I'm just going to use, I'm going to come up with a function. that it's a rational function, like for example, a simple one. I just made one up. And I'm shutting this book, putting it away. Okay, so then this is a rational function, and we are asked to graph and determine everything. Meaning first derivative, second derivative, increasing, decreasing, everything possible. So the first thing I will do, I will factor the numerator. But also separate the fraction. These two will have different applications, different purposes. So bear with me. X squared over x minus 1 over x. And when I simplify here, I get x minus 1 over x. This will be used for something. This form will be used for something else. Obviously, the function is not defined at 0. So therefore, its derivatives will not be defined at 0. I know the function has negative 1 and 1 as x-intercepts. I also know that this function f of negative x will be negative x squared minus 1 over negative x, which will be negative x squared minus 1 over x, which is the opposite of the function, so the function is odd, keeping that in mind. Now, I want to determine this, 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 and this, and then I can go to the first derivative. So the limit left and right here of this function, so let's find the limit. As x approaches 0 from the left, from x minus 1, x plus 1 divided by x. I know it has to be an infinity. So 0 from the left, negative, positive, negative. 0 from the left, negative, positive, negative. 0 from the right, point 1, negative, positive, positive. Now the limits at infinity, I'm going to use the fact that, and I'm just going to explain that right now. This rational function has degree 3 in the degree 2 in the numerator and degree 1 in the denominator. This function will not have horizontal asymptote, but slant asymptote. That's the reason why, another reason here why I wrote this. The slant asymptote is this, the quotient. The quotient of this division, which is just x in this case, is the horizontal asymptote, the slant asymptote. This is a linear function with a positive slope. The function itself has to follow that to infinities, to negative and positive. Very easy to determine that. The limit as x approaches negative infinity of this is negative infinity. Let me write it. Limit of x minus 1 over x as x approaches negative infinity is negative infinity. The other one would be positive infinity. Limit as x approaches infinity, x minus 1 over x is infinity. We know it has to follow the asymptote. I have completely done with the function. There is nothing else I can find about the function. X and y intercepts, I cannot plug in 0. Vertical asymptote. So x equals 0 is a VA. Y equals x is a slant asymptote, so I don't forget. And then somewhere I also write that the function is odd, so I don't forget. Now I have to study the first derivative. Not difficult because of this form. So when I differentiate to find f prime, f prime is 1 minus plus, because remember when I differentiate this we have negative 1 over x squared but plus 1 over x squared, so this is x squared plus 1 over x squared. No problem, always positive, never 0. Very nice. No critical numbers, no max min, the function is always increasing. So let me make sure that these two rows work well together. That's how I catch my mistakes. Okay, from negative infinity to 0 to infinity, of course. Awesome. From negative infinity to 0 to infinity, awesome. Done. All I have to discuss now is the second derivative. When I differentiate for finding the second derivative, this prime, 0. This is x to negative 2. Negative 2, x to negative 3. So this is negative 2 over x cubed. But remember, I prefer looking at negative 2 over x squared times x. Because when I study the sign, I will only study the sign of negative x, which is positive to the left-hand side and negative to the right-hand side of 0. Holds water? It does not. Very nice problem. I picked it. I'm kidding. When I graph a function with asymptotes, I have to graph the asymptotes first. Vertical, slant. I know how to graph this. Okay. Ready? From negative infinity approaching the asymptote, crossing at negative 1, 0, going to positive infinity on the left-hand side of the asymptote, vertical asymptote. From negative infinity approaching the slant asymptote, crossing, approaching infinity. On the other side, it has to be identical in the sense that it opens downward. It has to be odd, so everything has to be the same on the other side. So 1, 0. I don't even need the table anymore because the function is odd. And this is the graph of f of x equals was x squared minus 1 over x.